So let's talk about statistical power. But first, a quick review of hypothesis testing decisions from earlier. So when you do hypothesis testing, there are four possible outcomes that can occur. Right? Remember this matrix. Two are correct decisions, retaining the null when it's true, rejecting the null when it's false. Those are the correct decisions. And then there are two incorrect decisions, right? So there's rejecting the null when it's true. We call that a type 1 error. That's saying there's an effect when there really wasn't one. Second one is type 2 error. That's retaining the null when it's false. That is saying nope, no difference, no relationship when really there was. Okay, and so type 1 error is your alpha level. Type 2 error is beta, but really we talk about power. So how do we maximize the likelihood we are going to be in one of these green boxes in our research? Well, we aim for low alpha and high power. Low alpha, high power. So statistical power, brief review, is your probability of finding a difference or relationship when one does indeed exist. It's your ability to detect an effect that's there. Good studies have both low alpha, that is, they have a low type 1 error rate, and they have high power, which means you have a low type 2 error rate. So there are 8 factors generally that affect your statistical power. It's effect size, sample size, alpha level, the directionality of your hypotheses, that is, are they two-tailed or one-tailed, your study design, between or within, the relative sample sizes of your IV groups, are they equal or not, your inferential statistical choice, do you pick a parametric stat or a non-parametric? The parametric are more powerful. And finally, the precision of your study variables. Did you measure things precisely and manipulate them precisely? So number one, your effect size. That is the size of the relationship between the variables in your study. So how big of an effect do you expect in your study? How big of an effect do you think the IV is going to have on the DV? Will the differences between the IV groups be small, or will they be medium? Or are they going to be big? So for example, you could compare chicken eggs to duck eggs, and that would be a small effect size. If you look at the picture, duck eggs and chicken eggs are very similar in size. They are on average, the duck ones are a little bit bigger, but to detect that, it's much harder to do so. You have less power for smaller effect sizes. If instead, the opposite end of the spectrum, you would compare a hummingbird egg versus an ostrich egg, you would need a big sample, right? It's kind of obvious. It's that tiny little thing on the far right in the other picture versus the ginormous one. So, or actually it might be the middle one. But regardless, you see it's a huge difference. It's a large effect size, and it's easy to detect. So the bigger the effect size, the easier it is, the more power you have. So larger effect sizes are easier to detect, and that means more power than smaller effect sizes. Number two, sample size. So what's sample size? That's the number of participants in your study, okay? So folks seem to kind of know this one, bigger sample, more power, but let's just do it. So larger samples provide more precise estimates of the DV, kind of like the Skittles bag. A bigger bag, you'd get closer to that 20% than a smaller bag. Which is my example right here. So you can get a gigantic bag, and you know what? You're probably going to get 20% of each color in those huge bags versus the normal or the tiny snack size one. So because larger samples have less random error, that is sampling error from sample to sample, they have more power than smaller sample sizes. So how about alpha level? So alpha level, again, is your type 1 error rate of your study. Your likelihood of making a type 1 error is your likelihood of rejecting a true null, so screwing up in that particular way. Using a larger alpha makes it easier to reject the null, right? So if you think about it, if you use an alpha level of 99, you've got a really high 0.99. You've got a really high chance of rejecting null. But you're probably going to make a type 2 error, right? It's really easy to screw up the other way and say there's an effect or difference when there really wasn't. So larger alpha does make it easier to reject the null. There's a bigger rejection region. So using 0.05, it's easier to reject the null than alpha of 0.01. So a larger acceptable type 1 error rate means you'd have more power because you're more likely to reject the null, period. You have more power, I guess is the simple way to say that. But this is a problem on its own, right? Because yeah, you reduce your type 2 error rate, but you pump up your type 1 error rate, and you don't want to do that. There's a balance. So this is going to be the one I say don't do. So using a large alpha defeats the goal of having low alpha and high power, right? You got to balance those things. So it's best not to increase your alpha. How about directionality? So this is, do you have one-tailed or two-tailed hypotheses? So are you hypothesizing, there's going to be some difference, any difference, or you say, no, it's going to be this direction. They'll be lower, they'll be higher, it'll be a positive or negative. So it's easier to reject a null with one-tailed test than two-tailed tests, turns out, because all that rejection region is combined into one side of the distribution, one tail, hence the name one tail. And so one-tailed tests are more powerful. So having one-tailed tests, however, must be justified by your lit review. That's why you do one on your dissertation. So most of your hypotheses in your dissertation are going to be one-tailed, and that will give you more statistical power, more ability to reject the null when you should. So one-tailed hypotheses, it's easier to reject the null, justified, and that means you have more power than two-tailed hypotheses. How about study design? Is one of these designs more powerful? You bet. So between or within? So do you have the different people in the levels of the IV, or do you have ones that are the same people, or they're matched, or they're paired in the levels of the IV? That's basically your study design choices. So it turns out within groups designs, because they have the same or paired or matched people, they tend to have less variability just due to chance differences between people. They're more similar. In fact, when they're the same, it's the best of all. So better comparability between the people in your IV levels, it means less noise, right? They're not just giving different responses because they're different people. It's the same dang people, they're just under different conditions. So it reduces the just sort of noise or random variation. It would be the fancy way of saying noise. So from least to most noisy is repeated measures designs. You got literally the same exact people in the levels of the IV. Those are the most powerful. Then paired ones, right, where they're somehow like related in some way. They tend to be more similar than just two randomly chosen people. So paired is the next most powerful. Then matched designs, where you've somehow equated them on some important variable and matched them. They're different people, but you match them. And then finally, between groups designs are the least powerful, but easiest to do, honestly. So within groups designs, however, have some problems of their own. We'll talk about in the future. There's mortality over time. People drop out is what that means. Within groups designs are less noisy, measuring the dB, so therefore they are more powerful than between groups designs. How about relative sample sizes of the groups in your IV? So do you have unequal numbers of people in the different levels, or do you have the same numbers of people in the level? Which one do you think is more powerful? Well, smaller group sample sizes provide less precise estimates of your dV. So if you got groups that are different sizes, the smaller one has got more error than the bigger group. And so the smaller group introduces more error in comparison to the larger group. So equal IV group sizes, that gives you equally precise estimates of the dV for all of the IV groups, and that gives you more power than unequal. So the take home here is it's best to have the same number of people in each level of your IV. So they're all 30 or they're all 100 or whatever, but not one's 50 and one's 25 and one's 100. That would be bad because you have less power. So how about your inferential statistics choice? So remember that there is an inferential statistics or the bottom row of the matrix of inferential statistics, and then there's a backup weed whacker one above it. Is one of those choices better? Well, yeah, there's a reason we use these parametric tests. They tend to be way more powerful. And so, but you can't use them unless those statistical assumptions are met. So parametric tests, that is the bottom row of the matrix of inferential statistical tests. They use means and standard deviations, which take into account the magnitude, remember that, from back in scales of measurement. And therefore, they're more sensitive to smaller dB differences. They give you more power. So parametrical statistical tests are more sensitive to dB magnitude, and so therefore they're more powerful than non-parametric statistical tests. Finally, precision. So how precisely did you measure things in your study? Well, this is kind of a no-brainer, but if you imprecisely measure things or you imprecisely manipulate your dV, you introduce random noise again into your study, so that's bad. So consistently manipulating or measuring things reduces your variability in your dBs. And using reliable and valid DV measures provides better precision for your DV. And consistent manipulation and measuring of your IV. So for example, if you're comparing training, you make sure everyone's doing therapists, you make sure they're doing therapy all the same way, so there isn't differences between people due to other reasons besides type of therapy. So you train them all the same, that's going to give you more precise measures of the DV and a truer effect of the IV. There's going to be less noise. So, like using a mouse versus using your fingers. So using more valid, reliable, and consistent manipulation and measures of the IV and DV equals less noise, and that gives you more power than things that are invalid or unreliable or inconsistent. So use validated measures for your DV and make sure you do the IV manipulation the same each time. Next sort of topic, totally related, is statistical validity, which falls as a part of research validity. So research validity is an overall topic. It's sort of about the accuracy of research conclusions that you reach. So the goal of doing research is to have research validity, that is reaching the correct conclusions at the end of your study based on your stats. And there are 4 different types of research validity to consider. We're going to cover one of these in each of the subsequent weeks. There's statistical validity, that's today, when statistical results lead to accurate conclusions about the relations among study variables. And that is basically you've minimized your type 1 and type 2 errors. Then there's internal validity, which we'll talk about in a week, and that's when DV differences are primarily attributable to the IV that you studied and not other factors. So what's that mean? Well, it means you've controlled sources of confounding, right? So if there's differences between the groups, you know it's the IV that caused those differences. Then there's the long one, construct validity for causal conclusions. And this is when the underlying theoretical constructs for study causes and effects are correctly manipulated and measured. So that is when your operational definitions of the study variables are reliable and valid. We'll talk about that in 2 weeks. And finally, external validity, probably the least important, but this is when your study findings generalize to other samples, settings, procedures, manipulations, times, etc. This is when your study findings are replicable across variations in procedure and samples, etc. So today we're going to talk about statistical validity. So again, it's statistical validity is when your statistical results lead to accurate conclusions about the relations among your study variables. Poor statistical validity is when type 1 and type 2 errors have not been minimized in your study. So poor statistical validity is one of the big explanations for why the findings of studies can't be replicated. So if someone finds something in a study and no one else can replicate that, often it's because they have poor statistical validity. So good statistical validity means you need to reach the correct conclusion based on the data. So that's achieved by having low alpha and high statistical power. That's why this topic is thrown in with statistical power this week. And it's a balance, right, between alpha and beta error. So what are some of the threats to statistical validity? Well, one is a high type 1 error rate, that is a high alpha. That makes it more likely you're going to make type 1 errors, right? If you use the alpha level of 0.5 instead of 0.05, means you're more likely to reject a null when you should not. So that's poor statistical validity. So for example, let's say you use alpha of 0.25 or alpha of 0.10 because your study is otherwise underpowered. Well, you're more likely to reject the null, okay? So that is more likely to make a type 1 error though, unfortunately. So although it increases your type 2 error, or decreases your type 2 error, it increases your type 1 error. So there's something called family-wise type 1 error inflation, and this is when you don't adjust your alpha level for the fact that you're doing multiple tests in a study on the same data, and those tests are not independent. People do this frequently and make this mistake. So same data and you do a bunch of different tests on those data, it increases the likelihood you will make a type 1 error across the family of those tests. So what am I talking about? So it turns out type 1 error rates are additive across families of statistical tests, and that leads to family-wise type 1 error rate when you sum them. That is much higher than what you think your alpha level is. So if you have 25 variables and you do all possible pairwise correlations, each one of those you evaluate at a sig of 0.05, but that's 300 different tests. So 300 times 0.05, your type 1 error rate for each one. That's 15. That means of your 300 tests, you're going to say that 15 of them are significant when they really weren't. Okay, you're going to make a type 1 error. You're beyond like 1% or 100% probability. You're going to make 15 wrong decisions in 300 tests because it's additive. It's 0.05 times 300. You get 15. So also fishing for significance is a problem, and this is when you calculate additional tests in your dissertation to find something significant because maybe your original research hypothesis wasn't supported. This happens all the time where people do this. Like they do their dissertation, it didn't work out, so they just keep doing a bunch of more tests. That's called fishing, okay? And it also reduces your statistical validity. It inflates your type 1 error rate because it results in type 1 error rate inflation. So low statistical power, that is a high type 2 error rate, is also a threat to your validity, right? So making type 2 errors is also not reaching the correct conclusion based on your data. So for example, failing to consider those 8 factors for statistical power and the stuff we just talked about prior in the lecture, yeah, that's a problem. That reduces your statistical validity. So you have to make sure, first of all, you have good power by considering those 8 factors. Another thing, sort of related, we talked about it before, but it's restriction of range. So restriction of range reduces your statistical validity. That's when you reduce the full range of one or more of your variables under study, such as, for example, by correlating the IQ and grades among only honor students. So remember what happens when you do restriction of range and correlation? It attenuates the relationship. You get a smaller relationship than you think or than is true. So the example up top there where on the left in the full population there's a strong positive relationship. But let's say you just picked really smart people and really people with really good grades in your study, like picking honor students. You end up with the thing on the right where it looks like there's no relationship when in reality in the full population there is. That's going to lead to a type 2 error, and that is going to reduce your statistical validity. Another thing you can do that messes things up in terms of your statistical validity is violating the assumptions of your inferential statistical tests. So for example, these assumptions that have to be true for your parametric tests, if you violate them, it leads to them not working correctly, right? And so you get incorrect results that will be a threat to your statistical validity, will mess up your power. So if you imprecisely measure or manipulate things, that also decreases your statistical validity as well. That is not measuring things precisely and not manipulating things precisely or well. So for example, if in a study of attractiveness, that's your IB, you operationally define it as pictures of people, maybe they're smiling in one or not in the other, like the example above. But let's say that in reality, people don't actually see much difference in the picture. They don't notice it. It's not sort of salient enough. That would reduce, that is a poorly manipulated IB, to put it that way, and you have reduced your ability to detect the effects of attractiveness or not, I guess, on your study sample. So you've not manipulated things well. So another example for your DV anyway would be using a homemade measure of your DV. So you guys aren't experts in making questionnaires, so you're likely to make something that's less valid and precise than using a standardized, reliable, and validated scale. So these are all threats to type 2 errors, or increase your likelihood of type 2 errors, and so they're threats to your statistical validity. So finally, let's be positive. What are 8 ways to improve your study's statistical validity? Study big differences in your DV. So, like in my world, I can increase my effect size by looking at big differences in doses rather than small differences in doses. It's easier to detect the effects of bigger differences in doses. So you can do sometimes the equivalent of that with whatever your study is about. You could, increase the sample size. So that's one most people seem to know. You get more people in your study, all things being equal, you'll have more power. So theoretically, you could increase your alpha, okay? So you could increase your alpha. Unfortunately, that increases your type 1 error rate, so don't actually do that. So You could use directional hypotheses. So do a good lit review so that you have a alternative hypothesis that's directional that will give you more power. You could use a within subjects design. So if you could figure out a way to do a within subjects design, you have less error in your measurement of the DV. And another hint, you don't have to collect data on as many people. So within designs are the bomb. Number 6, you can get equal sample sizes for each level of the IV. Again, it's better to have equal sample sizes in the levels of the IV, so 30 in each group, not 50 in one and 30 in the other. It's better to keep getting folks till you have equal groups. Use parametric tests. That's why we cover them in the class. They're more powerful. So if you can, use a parametric statistical test instead of a non-parametric one. And finally, use valid, reliable, and consistent measures and manipulation of your IV and DV. So you could use, for example, DV measures that have more items. You could use IV, not just one example of your IV manipulation, but multiple examples that you expose people to. Don't make your own measures again, and pilot test your IV manipulation to make sure it works. So these are all good ways. Remember this when you're working on designing your dissertation next semester.